Processing raw, unsorted data expends massive computational energy locating elements. But when that data snaps into strict alignment, searching through it becomes almost effortless. We call this process sorting, the systematic arrangement of data into a specific, predictable order, most commonly strictly ascending or descending. It reduces the time required for every data retrieval operation that follows. This split-screen visualization demonstrates the impact of that trade-off. On the left, an unsorted list forces a linear search, checking elements one by one. On the right, a sorted list allows for a binary search, splitting the dataset in half with each step. For an array of 1,000,000 items, a linear search may require 1,000,000 individual checks. Because a sorted list allows for logarithmic search, the same result is reached in just 20 comparisons. However, binary search is mathematically dependent on this order. Without perfectly sorted data, the logarithmic efficiency of the search is impossible to achieve. Arranging data is the strict mathematical prerequisite that allows software architectures to scale. To handle the varied constraints of real-world computing, engineers rely on a specific taxonomy of sorting methods. The first decision in selecting a sorting algorithm is dictated by physical hardware, specifically where the data resides during processing. This diagram illustrates internal sorting. It is the ideal state, where the entire unsorted dataset is completely enclosed within main memory. Because everything sits in RAM, the processor can read and swap elements with direct access speeds, never pulling from slower physical drives. But constraints emerge quickly at scale. If you are processing a 100 gigabyte database on a server with only 8 gigabytes of available working memory, the internal sorting model is physically impossible. This limitation requires external sorting, forcing the system to rely on the slower storage disk. The algorithm reads a small chunk from the disk, pulls it through the bottleneck into RAM, sorts it, and writes it back. It repeats this until the entire database is processed. To manage this specific hardware constraint, engineers typically deploy a specialized algorithmic solution called external merge sort. Physical hardware limits dictate the software approach. The scale of the input data forces the first major split in our algorithm taxonomy. Returning to data small enough to fit inside RAM, we encounter the second major classification node, the preservation of original sequences. This introduces the concept of stable sorting algorithms. Notice duplicate primary values, a 50 tagged A and a 50 tagged C. A stable sort reorganizes the array sequentially. The identical 50s move down, but their original relative order is preserved. A remains above C. Stability ensures secondary data relationships are not scrambled. This is an unstable sorting outcome. The numbers are still in numerical order, but the algorithm swapped the relative positions of the identical elements. The C is now above the A. Merge sort, insertion sort, and bubble sort are mathematically designed to be stable. Standard quicksort and selection sort are inherently unstable. If you need to group a list of employees by department, but you want to maintain their alphabetical arrangement within those departments, stability is a strict operational requirement. The final theoretical divide dictates the actual mechanism the algorithm uses to evaluate the data. The most common approach is comparison-based sorting. This method pits two elements against each other using greater than or less than operators. Because of the logic required to compare across an entire array, general-purpose comparison algorithms hit a mathematical floor. They cannot execute faster than omega n log n time complexity. Surpassing this logarithmic lower bound requires moving away from direct element-to-element comparison entirely. This is achieved through non-comparison sorting algorithms, which include methods like counting sort, radix sort, and bucket sort. Here, the algorithm processes the input without using greater than or less than operators. Instead, it drops data directly into predefined logical groups. By bypassing direct comparison, these algorithms can achieve linear O of n execution times, but only on specific data types with narrow, predictable ranges. Moving past the omega n log n complexity floor requires a sacrifice in universal applicability. Developers trade the general utility of comparison for the specialized linear speed of counting and bucket methods. In standard programming, engineers rely almost exclusively on internal comparison-based sorting algorithms. We evaluate these using a standardized matrix, mapping time complexities across best, average, and worst-case scenarios. The top 3 rows, selection, bubble, and insertion sort, are simple sorts. Their primary failure point is the average and worst-case complexity, sitting at an inefficient O of n squared. An O of n squared constraint means the processing time scales quadratically. If the data doubles, the processing time quadruples, making these algorithms unsuitable for enterprise-scale arrays. Merge sort and quicksort, occupying the bottom rows, are classified as efficient sorts. These algorithms operate at the mathematically optimal O of n log n boundary for their average cases, effectively handling larger datasets. While simple O of n squared sorts fail under heavy loads, they require almost zero additional memory overhead. For microdatasets, a simple sort is often faster and leaner than its more complex counterparts. Utility in computer science is entirely dependent on context. This taxonomy tree maps every variable into a single decision-making framework. The algorithm you deploy is dictated by physical memory availability, the necessity of relative order, and the computational evaluation mechanism. The governing rule of algorithm selection is to never deploy a heavy algorithm for a lightweight problem. Arrays with small data footprints should utilize basic simple sorts. Massive arrays demand the logarithmic efficiency of merge or quicksort. Choosing the correct sorting logic is the foundational step. It governs the speed, memory usage, and ultimate success of the entire data processing architecture. To apply this taxonomy to reality, we must look at how these instructions run on hardware. Next, we deconstruct the pass-by-pass mechanics and specific space-time footprint of selection sort.